Hello everyone. Today we are discussing the concept that is the DC characteristics in operational amplifier. So here this DC characteristics indicates that in an op amp if there is no AC signal applied to the input terminals of operational amplifier, then according to theory the output voltage should be 0. Okay, so with no applying of input signals, the output voltage must be 0, but the output voltage will be a non-zero because of certain parameters. And what are those parameters and how that parameters will depend on DC signal? Okay, so those parameters are input bias current, input offset voltage, input offset current, thermal drift, and output offset voltage. Okay, so these are the 5 parameters that will affect the output voltage of an operational amplifier even if the input signals are 0. Now, what are the effects and how we will overcome those effects, and what are the compensation techniques that are used in order to obtain the 0 output voltage even if the input signals are 0, means even if the input signals are not present. Okay, now we will going to see the first parameter, that is input bias current. So in this we are going to see what is input bias current and how it affects the operational amplifier, and thereafter what is the compensation technique that is used in order to get the output voltage 0 if there is no presence of input signal. Now let us see the first parameter, that is the input bias current. Okay, so now the input bias current, as we know that for an ideal op amp, the input terminals does not draw any current because of infinite input impedance. Okay, and the block diagram of operational amplifier consists of a differential amplifier at the first stage, which is constructed by using either BJT or a FET transistor. Now we are seeing the BJT type of differential amplifier. Okay, so for proper biasing of these transistors, it requires the small amount of current from this DC source. Okay, so if we consider for a practical op amp, the input terminals draw small amount of current from the DC source in order to bias the transistor, even though the transistors Q1 and Q2 are symmetrical in nature. Okay, but these transistors will draw different currents due to the mismatches present in the input signals. Now let us consider that the bias currents present at the input of an op amp terminals or IB, indicated with IB, and if the bias current will present at negative terminal, name it as or notate it as IB minus, and if the bias current will present at positive terminal, then name it as IB plus. Okay, now the input bias current is defined as the average of currents IB minus and IB plus. Okay, so now we can write the equation of input bias current as IB is equal to IB plus IB minus by 2. So this is the average of two bias currents that are drawn at the input terminals of an op amp, which is defined by an input bias current. Now we will see what is the effect of input bias current will present whenever the input signal is 0. Okay, which means that the no input signal is applied. At that time, what is the output voltage of V0? Okay, now see what is the effect of input bias current to the operational amplifier. Now here we can write this output voltage expression V0 is nothing but the voltage drop across the resistor RF. Why? Because here no input signal is applied, that is no AC signal is applied to the operational amplifier, so the current flowing through the resistor will be 0, and here only current flowing through this is IB minus, that is a bias current at the inverting terminal. Okay, now if you apply KVL, then this is the path direction. Okay, so here the current entering at the resistor RF is in this way. So we can write the V0 expression as IB minus into RF. Okay, so the output voltage V0 is IB minus into RF. Now, if you consider for a typical value, so for an IC 741 op amp, the typical values of input bias current is 80 nanoamperes and the value of feedback resistor RF is 1 mega ohm. At that time, the output voltage V0 will be 80 nano into 1 m, which is equal to 80 millivolts. Means for zero input signal, the output also must be zero. But due to input bias current, the output voltage equals to a non-zero value. So whenever we are measuring the output signal in millivolts, this becomes a serious issue. This problem can be rectified with the use of a compensation resistor at the non-inverting terminal of an op amp. So how we are using a compensation resistor and what is the value of compensation resistor should be present in order to obtain the zero output voltage when there is no input signal applied to the non-inverting terminal or an inverting terminal, we are going to see. Now consider a inverting bias current compensation. Okay, so here the name inverting indicates that the input signal is applied to inverting terminal of an op amp. Okay, and here we see that our compensation resistor is connected at the non-inverting terminal, and we have to find out what is the R compensation value that should be present in order to obtain a zero output voltage at the output of an operational amplifier. So now for this circuit we have to find out what is the R compensation value. Okay, so here we are indicating the V1. So this V1 is nothing but the voltage drop across the resistor or compensation. And here for an ideal op amp, the virtual ground concept will be applicable. Now what is the virtual ground concept? So the node voltages at the two input terminals of op amp will be same. So here at the non-inverting terminal, the node voltage is V1. So this V1 will be same at the inverting terminal. Okay, and here this minus indicates that it is applied at the inverting terminal of op amp. Okay, now by applying KVL at the output loop, that is simply by applying KVL in this direction, find out what is the output voltage V0. Okay, so we can write the equation as minus V0 plus V2 minus V1 is equal to 0. So finally the V0 expression is V2 minus V1. So with the absence of input signal Vi, the V0 value will be V2 minus V1, indicates that this V0 will depends on V2 as well as V1. So if you maintain the condition that is V1 and V2 voltages are same, then we get the output voltage V0 value will be 0. So for this purpose, we have to choose the value of feedback resistor RF and R compensation in such a way that this V1 and V2 voltages are equal, which makes the output voltage V0 value to be 0. Now we have to see how to derive the R compensation resistor value and finally what is its value. Okay, so in general, for this circuit, we are assuming that the bias currents at the inverting terminal and the non-inverting terminal are same, which means that IB minus and IB plus are equal. Okay, now what we will do is at first we have to prove that this V1 and V2 voltages are equal. Thereafter we can find what is the value of R compensation resistor. Okay, now we are going to see the first proof, that is V1 and V2 will be equal. Okay, so now what we are assumed, that is IB minus and IB plus are equal. Now we can write this IB plus equation from the Ohm's law as IB plus is equal to voltage by resistor, that is V1 by R compensation. Okay, so consider this as an equation 2. Now simply apply the Kirchhoff current law at the node voltage V1. So what are the entering currents at the node voltage V1? It is minus I1 and I2 are the node entering current. So we can write minus I1 minus I2 and the leaving current is IB minus. So finally the IB minus value is I1 plus I2. Let us consider this as equation 3. Now what is the value of I1 and I2? So this I2 is nothing but the current flowing through the resistor RF. Okay, so here V2 is nothing but the voltage drop across the resistor RF. So from the Ohm's law we can write I2 as V2 by RF, and I1 is nothing but the voltage drop across the resistor R1. So we can write I1 as V1 by R1. And also we know that V0 value is V2 by V1, V2 minus V1, already we have defined in the previous slide. Okay, so for the input signal Vi is 0, the V0 value must be 0. By assuming that condition, we can define or we can prove that the V1 and V2 will be equal. After finding this condition, we have to find out the R compensation resistor. So from equation 5, we can substitute this V2 in terms of V1. Okay, so I2 we can write as V1 by RF. By considering that I2 as V1 by RF. So finally the IB minus we have defined, that is I1 plus I2. So I1 is V1 by RF and I2 is V1 by R1. So finally IB plus or IB minus is V1 into R1 plus RF by R1 RF. Now from the equation 2, that is what is the equation 2? That is IB plus is equal to V1 by R compensation. Simply equate those equations, then finally we will get the R compensation value is R1 RF by R1 plus RF, which is nothing but the R1 is parallel to RF. So this is the value that we have derived. If you maintain this R compensation value, then we will get the voltages V1 and V2 are equal, in which in turn makes the output voltage V0 to 0 if there is no presence of input signal. Thank you.